and we'll get going. All right. Okay, so thanks again for joining us. My name is David Candell. I am a regional application consultant for Belimo. Belimo has a special segment of its sales team that does the same job I do, and we don't sell anything to anybody. Our job is completely to educate our customers about advanced technology and help better understand their applications and what we can do to better serve our customers. So if you have a question in your area, please feel free to reach out to Belimo. We likely have either myself or someone in your general area who can help you out. So let's get started today. We're going to talk, this is actually the third webinar in a three-part series regarding the Belimo Energy Valve. We talked in the last session about delta T management as a way to conserve energy. Today we're going to talk about advanced control strategies. The Belimo Energy Valve has the ability to operate in what's known as flow control mode and also in power control mode. And so today we're going to go through those two types of advanced control strategies so that you all better understand what that means and what they can do for you in terms of control and better operation of your facilities. So let's get started here. I always like to point out how valves have changed over time in terms of how we control them and what the changes really are. So let's start with the sort of most basic valve, and we'll call these types of valves position control valves. And what's pictured here on your screen is a cutaway of a Belimo CCV, or characterized control valve. And what it is obviously a ball valve with a characterization disc in it that allows it an equal percentage flow characteristic. Just as easily could have put a picture of a globe valve in here, also considered a position control valve. Now the reason we call them position control valves is as follows, is that the control signal drives the actuator, but it is only driving the position of, in this case, rotating the stem. So if I give it 50% control signal, it's going to rotate the stem 50% of the way and create an opening through which the water needs to pass through. However, we can all kind of agree that if I have a specific opening and there's 1 psi of water pushing on that opening, I'm going to get a dramatically different flow rate than if the same opening saw 50 pounds of pressure. Now granted, that's a humongous swing. We hopefully aren't seeing those in our buildings, but it certainly illustrates the point that controlling directly to the position of the valve may or may not have the best value in terms of controllability. And so we'll put that sort of on the low end of technology. Now we've been using this technology for darn near 100 years, so it's not like we can't figure out how to control a building with it, but frankly there's better options today. So let's take a look at the idea of flow control. Another word for flow control would be a pressure independent valve. And the reason we call this type of technology flow control is that if I send a 50% control signal to this valve, and the valve you see here is the Belimo EPIV, or electronic pressure independent valve. If I sent a 50% control signal to this valve, well, the valve would interpret that as a specific GPM or flow value depending upon how it's programmed, and it would modulate the valve until it found that specific flow. So not all pressure independent valves work that particular way, but they all control directly to a flow amount instead of to a position of the valve. And this is so much closer to what we're interested in controlling. I honestly, for the control of temperature, I don't care what position my valve is in. I really am concerned about how much water is going through my heat exchange device, because that's going to control how much heat is exchanged and how many BTUs are delivered into a space. And that's what we're really after here. So flow control valves allow us to do just that. They allow us to control the exact amount of water that reaches our coils. So let's take a few minutes and discuss flow control and some of the benefits that it has, because frankly they're quite vast. So let's jump in to flow control. Now flow control, or pressure independent valves, are a little tricky to describe their advantages, because most of the advantages of pressure independent valves are the types of things that we assume would happen anyway. And so what we really need to do is examine some of the ways that pressure-dependent valves or position control valves, such as the CCV or the globe valve that are shown here on the screen, some of the ways that those don't behave like we would like them to. And so we're going to take a look at how we can generate low delta T's at the coil. And low delta T really means that we're transferring heat inefficiently. We're probably using more water than we have to achieve the same amount of load offset in the space. We're also going to take a look at certain scenarios where additional flow through a coil might not create any more heat transfer. Obviously, that's wasteful as well. And then at the end here, we'll take a few minutes and talk about static versus dynamic balancing, because standard pressure-dependent or position control valves are all statically balanced in the system. And we'll show you how that can create some issues. So let's start by talking about how we size a a position control valve, a standard pressure-dependent control valve. And this type of valve will be sized with the formula you see here. This says that the flow coefficient, or C sub V, is equal to the GPM of the coil divided by the pressure drop. Divided by the square root of the pressure drop. And so the GPM obviously is defined by the size of the coil. The coil will tell us how much water it needs based on its design. And the delta P is frankly going to be designed by a design engineer who's going to specify a certain amount of pressure drop allocated for each particular globe valve. So the question is, if I buy a valve, let's say I buy a valve that's 10 CV. Well, mathematically speaking, then the left side of the equation is always 10. That can't change. And so if I fluctuate my pressure on the right side of my equation, if my pressure drop is higher than anticipated, well, I'll have more flow than I anticipated, and obviously if the pressure drops lower, we'll have lower flow. So this is really the same argument we talked about earlier, but here's the mathematical support of it. Let's assume, because this seems to be the case, that the majority of pressure fluctuations tend to be over-pressurizing a loop, not under-pressurizing it. So let's assume here that we have an over-pressurization and then we overflow. We have more flow rate than we need. Well, let's take a look at a second equation here, and I'll give this a second to pop up for you all. There it is. Let's take a look at the power output equation for heat exchange at a coil. So if we calculate the load based in BTUs per hour, it's simply 500, which is a constant that makes all our units work out, times the flow rate in GPM times delta T in degrees Fahrenheit. Well, we just said that our GPM is going to be elevated because we have overflowed. Well, if my load doesn't change, so the left half of my equation is a constant number, well then the right half of my equation has to be a constant number. And so if my flow goes up, my delta T goes down. So this is what we call, mathematically speaking, two terms being inversely proportional. So 10% increase in flow requires a 10% reduction in delta T. And so you can see how we can easily get low delta T issued simply by over-pressurizing the control valve in our loop. So we've oversimplified this a little bit, but you certainly understand why overpressurization can cause some problems. One of the reasons that this overflow becomes a problem, or that we don't necessarily change the loading, we can see here by looking at a coil curve. So that's what you're looking at on this screen here. So we have increase in flow rate going from left to right on the bottom of our axis, and we're increasing BTUs per hour going vertically up the y-axis. So you can see that as I put more and more water into my coil, it starts to sort of flatten a little bit. So the curve's a little steeper at low flows, which means I'm transferring heat more efficiently. And then as we get to higher flow rates, it starts to have a, what am I trying to say here? I guess it would have a lesser slope to it. It's not really flat, but it's certainly flatter than it was at the beginning. But what happens if we overflow a coil? So in this case, let's say this coil is rated for 55 gallons a minute and is produced 325,000 BTUH, or somewhere in that neighborhood. What happens if I put another 10 gallons a minute through there, and I will show you that nothing good happens. Basically, I do start to flatten out my output, and that coil is only rated for 55 gallons a minute. If I put 65 gallons a minute through it, my heat transfer becomes very inefficient. And essentially what happens is I've pumped more water, or I've put more water into my coil, but I haven't increased the amount of BTUs that can be produced. And so this is another issue that we mentioned early on, that we can create an area in our coil where more water doesn't mean more heat transfer, and surely that's problematic. Let's take a look at the idea, thirdly, of static balancing versus dynamic balancing, and this is really where a flow control technology valve versus position control is going to give you a much greater advantage. So let's take a look. On your screen, what you're going to see here is a very simple, an oversimplification of a building, basically. And let's say that down at the bottom there's my pump, and that's going to be my distribution pump for my building. And we'll just call this building, say, a 10-story building. And the first floor of that building is represented by the first air handler coil, control valve and balancing valve that you see, and then there's some dotted lines, which would be the rest of the building, and then on the very top floor we would see our second coil valve and balancing valve. So we're looking at the first floor and the 10th floor of our building, and we're going to juxtapose those because they're going to have vastly different behaviors, even though in this case we're going to assume all the coils are identical, the control valves are identical, and the balancing devices are identical. And then the last thing I need to explain on this graph, or on this chart here, is that on the right-hand side we're displaying a couple of different delta P readings. And what you're looking at is the pressure drop across the branch run. So on the lower or first floor, you see that we have a 20 psi drop between the inlet to my coil and the outlet of my balancing valve. And at the top of my building, I'll only have 10 psi between the inlet to the coil and the outlet to the balancing valve. And the reason for that is that this is a direct return piping system, and so I have very high pressure water coming into the first run in my first coil, on the first floor rather, and then the water has to go all the way up the building, servicing all the other floors. We're going to lose pressure all the way there, and then on the way back down, we're going to further reduce the pressure, and by the time the return water gets back to the first floor, it's relatively low pressure. So we have a much higher differential on our first floor than we do on the 10th floor. So let's go ahead and balance this building as we would traditionally. So we're going to take a look and see that at our top floor, we have a 4-pound pressure drop on the coil, and then we have a 4-pound pressure drop designated for the valve based on the way we size the valve. And then we're going to adjust the balancing valve till all the flows work out correctly. And then when we do that, we will see a 2 psi pressure drop on the balancing valve. So 4 plus 4 plus 2 is going to give us the 10 psi that we see on the right-hand side. And so far away from the pump, we have relatively low branch differential, and so we have relatively low pressure drop on my balancing valve. Let's now take a look at the first floor. Now remember, the first floor has the same equipment as the top floor. So it's the same air handler, it's the same coil, it's the same control valve, it's the same balancing device. And so I still have a 4-pound pressure drop on my coil, I still have a 4-pound pressure drop on my control valve based on the flow, but when I balance the loop on the bottom floor, on the first floor, I'm going to have a substantially higher pressure drop on my balancing valve, and that would give me a 12-pound pressure drop down there. And so as we review what we've done here, when we're closer to where we're pumping, we have higher branch differentials, and in most cases, we have much higher pressure drop on our balancing device. So everything's identical in these two loops except the pressure drop on the balancing valve. So maybe we should go ahead and take a closer look at what makes a balancing valve work to understand the difference between having a 2-pound drop or a 12-pound drop. So I have my balancing valve here on the screen to the left-hand side, and on the right-hand side, I'm using this diagram here as the representative of a piece of pipe, and we're going to say that when the valve is fully open, the balancing valve, that the pipe is essentially unrestricted. That's probably not the case. I think a balancing valve, even when wide open, would have a little bit of a pressure drop, but we're just going to say for the purposes of this example that A fully opened balancing valve at 100% flow has no pressure drop through this pipe. So what we're going to do to generate the pressure drop, and if you remember, we needed to generate 12 psi of pressure loss on the first floor of our building. We're going to turn the handle of the balancing valve, and as we do that, we're going to constrict the opening of the pipe, essentially. So we're just creating a smaller area through which we want to push the same amount of water. And when we do that, 100% of the flow through this smaller area, in order to get all the water through a smaller area, it costs us energy in the form of pressure. And so we lose pressure there, and this is how we generate a pressure loss or a pressure drop, is by forcing this water through a smaller area. So to push 100% of the water through this reduced area of the pipe, we generate a 12-pound pressure drop. And that's wonderful at full flow, but what happens if we don't have full flow? What happens, for instance, if we only have 20% of the flow? How much pressure drop would be created by pushing 20% of the water through this reduced hole? And in terms of surface area, the surface area exposed by this reduced area is way more than 20% of the original surface area, and so physics kind of tells us that we'll have little or no pressure drop even though we have this reduced area. And this is the problem with traditional balancing devices. So if we go back to our building and we turn the pump down to 20% and then take a look at how our balance works, we'll see that we're going to run into a few problems. So now let's take a look at the top floor, and I will tell you that the top floor tends to not be the one that ever has an issue. But let's look at it anyway. So I've assigned a 4-pound pressure drop to this coil, mostly because it makes the math easier to follow as we go. In reality, that coil is only going to take 1 or 2 psi pressure drop at 20% flow, but we'll just call it 4. And the balancing valve was taking a 2-pound pressure drop. We will generously allocate 1 psi to that. It's probably closer to 0, but like I said, this zone is not the zone where I'm going to have a lot of trouble. And as we calculate here, all the remaining pressure goes to the control valve. And so we have 5 psi where we should have had 4, and so we're going to have some kind of small overflow at this far zone. I'll remind you one more time, the far zone, essentially it's either under control and it feels good in that space, or we're starving that coil. But we don't tend to have instability and control problems out there. We do tend to have them on the first floor. So let's take a look down here. So again, the same deal with the coil is that we're going to show 4 psi. That's probably generous. The balancing valve was supposed to take 12 psi pressure drop, and in this case, it's only going to take, like we said, 1 or 2. So we'll allocate 2 psi to that guy there. And then as we balance out the loop and do the math, the control valve, which was sized for 4 psi, now is getting 14 psi, and in this case we're bound to see a fairly substantial overflow in this valve. Now we're going to see an overflow at low flows, which really means that we're going to see a substantial increase in the amount of heating or cooling that's dumped into this space. So what happens in these types of zones is that we typically have trouble hitting our set points because we're overshooting them in both directions. And what it looks like is a control valve that's always hunting to hit the signal, and a discharge air temperature that's always a degree or 2 high or a degree or 2 low. And so these create unstable zones. What we just went through in terms of static balancing is described other ways from time to time, and you may have heard of something called valve authority. And valve authority is simply the ratio of the control valve's pressure drop to the pressure drop of the branch. And when you have bad valve authority, basically what you see on the first floor is exactly what happens. And so if you're more familiar with the concept of valve authority than you are static versus dynamic balancing, they're essentially the same explanation. So we said what static balancing is. Dynamic balancing is a whole lot simpler because dynamic balancing, everything works the way we want it to. So what we're going to do is we're going to put PI valves or flow control valves in all of our loops. And in the first floor or the top floor, we're going to get the exact performance you'll want. You'll notice that I haven't drawn a balancing valve on these. Well, flow control type valves, pressure independent valves, don't require balancing devices, and they don't need to be manually balanced. The valves by themselves are dynamically balanced, which means that they will adjust their flow to the pressure that's in the loop. Again, we're controlling to flow. We can now sort of ignore the pressures to a degree. So whether I'm pumping at 0 or 100% or anywhere in between, and whether I'm on the top floor of my building or the bottom floor of my building, I should get the same performance, and I should get the exact GPMs required at all of my branches. So as you can see, this flow control technology really allows us to get rid of this idea of static balancing, or really get rid of the idea of having the effects of valve authority disrupt our control. So if we take a look at a few points we talked about in regards to flow control, they're fully pressure independent, they're preventing overflow, they're dynamically balancing your loops. The Belimo Energy Valve has the ability to operate in flow control mode. In fact, it is by far the most common control strategy employed by the Belimo Energy Valve. But there's a second one, and I think we should take a look at it because it's quite interesting. We talked about position control valves and what those do, and then we talked about flow control on our chart here, and we defined what those can do. And I'm sorry, I'm skimming through this animation pretty fast. If your computers aren't catching up, I'll try to slow down here for a second. We went through flow control. And then the third, or the next step here, would be power control. So the Belimo Energy Valve has an integrated BTU meter that allows us to do our delta T management and allows us to be pressure independent using the flow capacities, but it also allows us to measure BTU. And when we measure BTU, that means we could control directly to how many BTUs are being produced. So we didn't like to control to the position because that didn't allow us to know really how much water was going to our coil. And we like the idea of flow control because that gets us exactly how much water is going to our coil. But what if we didn't worry too much about how much water went to our coil or even what the temperature of that water was, but we just modulated based on how much heating or cooling was being produced? And that's what power control is all about. So let's delve a little bit into power control. What you're looking at here on your screen is a drawing of that coil curve we looked at earlier. So again, we're increasing flow from left to right across the bottom of the screen, and we're increasing coil power in BTUH as we go up. And one thing you'll notice we pointed out a little bit before is that the curve is very steep at low flows and it flattens out at high flows. Well, this is kind of a tricky shape to control with a controller. And so what the control valve typically does is try to have an opposite shape. So I'm going to draw a control valve curve on here as well. This type of curve is either called an equal percentage curve, or sometimes it's simply referred to as a characterized curve. And you'll see we have a different set of axes. We're actually on the bottom from left to right, we're increasing the control signal, or we're increasing how open the valve is. And then on the vertical axis, we have flow. And I recognize that I have flow on both axes. I will clean this up here in just a minute. But valves open slowly to counteract the fast-acting nature of the coil itself. And the reason we do that is if we have control over the control signal, which we do, and what we're interested in is how much power is produced by the coil, which is what the output we're interested in. If we cancel flow out of both of these curves and combine them, we're trying to get something relatively linear, as we've shown here, because now our controller can say, hey, 10% more control signal anywhere in the range should generate 10% more coil power. And if my valve and my coil are perfectly matched, I have this type of control. If they're a little off, or the characterizations don't match, or one side's a little bigger than the other one, well, you still get pretty good control, but you're not exactly getting 10% is 10% more everywhere else. Well, the black line that you see on this curve here, which relates control signal directly to coil power, is power control. That's what the Belimo Energy Valve is available to do. What it does is it takes the valve and the coil and makes them into a single piece of equipment that we control directly to BTU exchange into the space. And it's linear in nature. So if we do an example of how power control would work, we'll say that we have 83 tons of air handler, because that happens to work out to 1,000 kilobtus per hour. So I have coil power in the range from 0 to 1,000 kilobtus per hour, and I have a control signal from 0 to 10. Well, if I have this, it scales linearly, which means if I give it a 3-volt signal, I'm going to get 30% of 1,000, or 300 kilobtus per hour, and 7.5 volts similarly would give me 3/4 of my allotted amount, 750 BTUH. So power control simplifies everything. It makes the control logic ultra simple. Where's the real value in this? Well, there's a couple of really nice values in having direct control over how much power is produced. We talk a lot about pressure independence, and we can overcome pressure fluctuations in our system, which we can, and it's very important. But what if we were able to overcome temperature fluctuations in our system? If my coil's designed around an entering temperature of 42 degrees on my chilled water coil, and suddenly the water comes down the pipe at 44 degrees, what happens? Well, I'm not going to produce as many BTUs because I'm going to have warmer water. My delta T is going to be a little bit lower, and I will likely disrupt my discharge air temperature. The discharge air temperature will be disrupted. The controller will notice that, send a signal to the valve. The valve will open a little bit further to allow additional flow at a slightly lower heat exchange to create the same amount of BTUs in that space. Well, the Belimo Energy Valve in power control mode can do all of this without involving the controller or disrupting the discharge air temperature. Since it's constantly sensing the delta T and the flow, it is measuring BTUs, and if the 42-degree water suddenly arrives at 44 degrees, well, the Belimo Energy Valve will recognize that it's not producing the required amount of BTUs and simply modulate the valve open to allow more flow to achieve the BTUs required to satisfy the space. And so power control can overcome small disruptions in the supply water temperature. There's a few other things that are quite interesting that you can do with power control, things like what we call strategic load distribution, which means I want to identify exactly how much cooling is allotted to any given space so that I'm not overcooling one space and undercooling another, and think about the potential options if you were employing a load shedding strategy to be able to simply tell your control valve to supply less cooling to the space at a given time. So there's a lot of different options there. So as we've looked at this today, we've looked at our advanced control strategies, and we looked at flow control, which makes us fully pressure independent, prevents overflows, and dynamically balances our loops. We can add on power control to that. And power control is pressure independent, but it's also temperature independent. And it makes the valve and the coil work as a single unit. And it still includes all of these benefits that we get from flow control, is that it will stabilize pressure stuff and prevent overflows, and it's dynamically balanced. And so we have a lot of really great options for control with the Belimo Energy Valve. If you'd like to learn more about the Belimo Energy Valve, I encourage you to go on to energyvalve.com. It's a pretty nice website, and there's lots of good technical information in there. There's case studies. There's even an estimated energy payback tool that's integrated into there. And I urge you to reach out to your local Belimo sales manager or your local distributor that sells Belimo products. And if you really want to learn a lot more about Energy Valve, ask them to set up an appointment with someone like myself, a regional application consultant for Belimo, and we'd be happy to come to your facility and do a full training. So if there are any questions, I'm going to bring Michaela back in now, and we can set up the Q&A box, and people can type in their questions.
Thank you so much, David. We actually have questions coming in. Can you hear me?
Yeah, yep.
Okay, perfect. So the first question we have is from California. How do we get feedback for our California Title 24 to reduce speed on the pumps just to satisfy the worst case load?
Gotcha. So California Title Title 24 requires that the differential, actually, I think it's a static set point in California, but the pressure sensor that drives your VFD has to be reset based on the position of your control valves. That's the simplified explanation. So Belimo Energy Valve communicates in a bunch of different ways. It has an analog output feedback like a standard actuator. It's also a BACnet capable device, and through any of those types of communication you can receive valve position, and that will allow for the employment of that strategy. Now, all of you who are not in California are saying, yawn, I don't care, but keep in mind there's very similar language in ASHRAE 90.1, and so if you live in a jurisdiction that's adopted ASHRAE 90.1, make sure that you're keeping an eye on that as well, because that's definitely a factor for the whole country.
Okay. Next question. When we use power control, we get better delta T performance. Is there a tipping point where I get too much delta T and the chiller would not be able to handle the extra absorbed energy?
In general, we want to design our coil delta T's to match our chiller delta T's. In other words, if you have a 16-degree chiller and you're generating 20 degrees of delta T and that 20 degrees is showing itself to your chiller, you know, you're going to get a reduced performance the higher that number gets. Now, I'm not a chiller expert, so I can't really tell you where the tipping point is, but typically when I work with customers, we're trying to match the plant is the goal. Because frankly, if I get a huge delta T at my coil, but I'm hurting my chiller while I'm doing it, it's not really an energy savings measure, because my pump costs will be less, but my chiller cost is going to go back up if I have too much inefficiency because the delta T is too high. But again, I would reach out to your chiller manufacturer rep to have that discussion.
Okay. Next question. How is this valve programmed, and how do you prevent laminar flow at low load conditions?
First part of that question is it can be programmed two different ways, well, three different ways actually. We have a little handheld device called the ZTH that can plug directly into this. You can also plug a laptop directly into the Belimo Energy Valve. There is a Cat5 plug on the back side, and the actuator it has a contained web server. So it has an IP address, and you can basically log into the actuator and program all your parameters. Most of those parameters can also be programmed directly through BACnet, so you could do that through your automation system. In terms of laminar flow through the coil, you got to be careful. Usually laminar flow through a coil takes care of itself because laminar water doesn't transfer heat very effectively. But I'll tell you this, it's pretty difficult to get water through everything and still make it laminar. That said, if it does turn laminar and you can't transfer heat very effectively, your discharge air will likely be disrupted. But you would have similar problems regardless of your control valve technology. So I don't know that any of this is unique to the energy valve.
Okay. Next question. What is the delta P we have to consider in the energy valve in order to calculate the head pressure pump?
Okay, so the energy valve is sold by GPM ratings. In other words, that valve on the screen is like a 2-inch energy valve. I think we can get it's like 75 or 80 gallons a minute through there. But the key is that you can get 75 or 80 gallons a minute through there at 5 psi pressure drop. So you don't need 5 psi to make this valve pressure independent, but you do need 5 psi to hit the maximum flow rate. Now, all Belimo catalogs contain a chart that will show you, let's say you buy that 2-inch valve, but you're only going to run it at 45 gallons a minute. Well, there's a chart in there that will tell you how much pressure is required to achieve 45 gallons a minute through that valve. So as you do your pump calculations, you're going to want to consider which valve is sort of your critical one, which one you're sizing your pump based on, and then take a look at the specific. But the short answer is if you size around 5 psi, you're done, but you can do a little better than that if you want to dig down into it.
Okay, one final question, and then we are going to end the question and answer session. If at a later time you should come up with a question or concern, feel free to email us at marketing@us.belimo.com. And once again, this webinar was recorded, so if you joined us partway through the webinar, we can surely send out that link, or you can find it on YouTube so that you can view it in its entirety. Okay, so last question. Will this be able to take a 4-20 MA input at a 0 to 10 VDC, and I assume a digital input to enable and disable? I also assume that this will operate in standalone mode with no DDC control system.
Okay, there's a bunch in there. You can always do 4 to 20. I would need to get you technical documentation on that. There's a way to do 4 to 20 on this, but I frankly, off the top of my head, I'm afraid to commit to anything for the entire audience. So we'll say it can be done, and please reach out to us. We can get you some specific information on how to do it. The second part of that question was what, Michaela? I'm sorry.
I also assume that this will operate in standalone mode with no DDC control system.
Okay. So in general, if you don't connect the DDC to the energy valve, there's no way for it to modulate based on any input. In other words, it only takes a 0 to 10 or 2 to 10 or 4 to 20, if you do it that way, input, and that needs to be generated by something. So we've had clients ask about putting it in, applying voltage to the input to drive the valve to its full flow position, and then using delta T management only to modulate the valve. But I don't think anybody's actually implemented that. As it is now, it's really advantageous to have it tied to your controller, because then you can modulate based on discharge air temperature, just as you would any other type of control valve.
All right. Thank you so much, David, and thank you everyone for attending today's webinar. We look forward to hearing from you and seeing you at the next session. Everyone have a great day. Thank you.